Welcome to the Explainer. Today, we're going to dig into a piece of math that, believe it or not, is running in the background of your daily life. We're talking about something called the first-order linear differential equation. So let's kick things off with a question you've probably never thought to ask. How does your coffee know how fast it should cool down? I mean, you've seen it, right? It cools off really fast at first, and then it kind of slows down. And the why behind that? It's all about the math. You see, the whole secret is how we can use mathematics to build a little story about what's happening in the real world. The answer to our coffee question actually comes from physics, from Newton's law of cooling, to be exact, and it's described by a really powerful kind of equation. Now, here's the core idea, and it's actually pretty simple. The hotter the coffee is compared to the room around it, the faster it cools. And as it gets closer and closer to room temperature, that cooling process just slows down. So the rate of change isn't some constant number, it's always changing based on what the temperature is right now. And the perfect tool for describing this kind of relationship is the first-order linear differential equation. It's basically the mathematical language we use for any system where the rate of change depends on its current state. You know, everything from a cooling cup of coffee to the way populations grow. Okay, so let's take a look at the standard form of this equation. I know, it might look a bit intense at first glance, but I promise, once we break down what each little piece is doing, it's all going to click into place. All right, let's meet the main characters here. That dy dx part, that's just a fancy way of saying the rate of change. So how fast our temperature, y, is changing over our time, x. We call it first order because we're only looking at that first derivative, nothing crazier. And linear, that just means our variable y is just y. It's not y squared or the square root of y or something weird. That's what keeps the math from getting out of hand. Now, these equations come in two main flavors, and it all boils down to that q of x part on the right. If q of x is just 0, we call the equation homogeneous. You can think of this as our coffee cup cooling in a perfectly sealed room with a constant temperature. It's a closed system. But if q of x is not 0, we call it non-homogeneous. That means some outside force is messing with it. Maybe a fan is blowing on the cup, actively changing things. So, how in the world do we actually solve these? Well, there's this really clever, kind of elegant method that uses a special tool called an integrating factor. And you can think of it like a magic key that's designed to unlock the entire problem for us. And this right here is the formula for that magic key. We build it using the pfx function from our original equation. The whole point of this integrating factor is to be the perfect multiplier that's going to help us tidy up the left side of our equation. And here's where the magic happens. Its entire job is to take that complicated-looking sum on the left and transform it into something super simple, the derivative of a single product. Now, why is that so great? Because integrating a derivative is a piece of cake. They basically cancel each other out. It's the one move that lets us solve for y nice and clean. Okay, theory is great and all, but let's actually see this thing in action. The best way to really get a feel for this method is to just roll up our sleeves and walk through an example together, step by step. So we're going to tackle this non-homogeneous equation. In this case, our p of x is just the number 2, and that external force, our q of x, is e to the power of x. We just have to follow these 4 steps. First, we figure out our integrating factor, our key, which turns out to be e to the 2x. Second, we multiply every single piece of the equation by it. Third, and this is the really cool part, the left side just magically folds up into the derivative of one simple thing. And finally, we just integrate both sides, and that lets us solve for our function y. And after all that, this is where we land. We call this the general solution. It's an answer that describes every possible solution to our equation. But hang on a second. What's that big capital C doing in there? That constant c is actually the most important part for understanding what our answer really means. You see, the solution isn't just a single formula. It's something way bigger. So that c is what we call the constant of integration. It shows up anytime you do an indefinite integral. And in the world of differential equations, it basically represents an infinite number of possibilities. So what this really means is that there isn't just one answer, one curve that solves our problem. No, there's an infinite family of them. For every different number you could possibly plug in for c, you get a brand new, perfectly valid solution, a different path that our system could take. So with an infinite family of answers, how do we ever pick the right one?
Well, we need one more piece of the puzzle. We need a starting point. And in math, we call that an initial condition. This is what takes a general problem and makes it specific to our real-world situation.
So for our example, let's just create an initial condition. We'll say that at the very beginning, when time is 0, the value of our function is 1. If this was our coffee cup, it'd be like saying, I know for a fact that when I first poured it, the temperature was exactly 100 degrees. It gives us a specific point in time to lock our solution onto. So now, all we have to do is plug those numbers, x equals 0 and y equals 1, right back into our general solution. After a little bit of algebra, we can solve for the one specific value of c that makes our curve pass through that exact starting point. And in our case, c happens to be 2/3. And here's the crucial part. Once we plug that value for c back in, we don't have a family of solutions anymore. We have the solution, the one single unique path that our system will follow because it's the only one that satisfies both the original equation and our starting condition.
And that really shows you the whole journey, doesn't it? We started with a real-world problem. We used this powerful math to find a formula that gave us infinite possibilities. And then with just one little piece of data, we narrowed it all down to a single predictable outcome.
And of course, this kind of math isn't just for cooling coffee. It describes how a capacitor charges in an electrical circuit, how radioactive material decays over time, how a population grows when it has limited food. It really leaves you with a final question, doesn't it? How many other things in the world all around us are being quietly guided by this same beautiful, precise logic?